What's going on, guys? It's the Unhinged Engineer here, back with episode 12 of our Georgia Tech OMSCS vlog. So today I want to give a comprehensive review of the last project of my first class. So that first class was AI Techniques for Robotics, and the project we're going to be discussing today is the SLAM project. So SLAM, if you didn't know, stands for Simultaneous Localization and Mapping, and we were tasked with implementing something called GraphSlam, which is one of the simpler versions of this technique for a drone trying to navigate like a forest of trees, right? That was the general premise of the project. Like I said, it was the last one, and given that SLAM was one of the two main topics that really motivated me to take this class, the other one being Kalman filtering, which is actually the first project, so nice bookends there. I'm really happy to say that I enjoyed this project. I think it was implemented well from the course's perspective. I think they did a great job. I'm really happy with how it went, the grade I got, and more importantly, what I learned along the way and what we were asked to do. So yeah, positive review overall to kind of give up a bit early, but let's get more into detail, right? So, like I said, we're doing GraphSlam for a drone in a forest. Basically, that drone is flying around the forest. In the first thing, it's kind of in the first part A, which is about like 60%. We're given motion commands, and based on those motion commands, we have to build a map and an estimation of our current position, right? So, again, to reiterate, we're trying to simultaneously localize ourselves, so determine where we are, as well as build a map representation of the trees in this forest, right? Which would be very simple if our measurements were all perfect and our motion commands were all perfect, but they're not, right? In the real world, we have noise, and that kind of begets the need for something like SLAM. And so what GraphSlam is about is building a matrix representation of local constraints, so like local relationships, distances between different bodies of interest that we can infer from our measurements and our motions, such that we have a solvable system of equations that we can use to figure out not the positions, not just of ourselves, but also of all the other trees and whatnot, right? So that's what we're asked to do. And yeah, like I said, part A, we're given motion commands and we have to build a map from them. Part B, we're not given any motion commands. We just have to use our SLAM that we just implemented for part A to build up a map of where the trees are and then construct a path to get from where we are to it's called treasure. So there's this like Indiana Jones pun going on. They call it Indiana Drones. So we're looking for treasure in this forest, right? And so we have to chart a path given this map that we've now built using SLAM. So you're literally pulling in all the functions you developed from part A to get from where we are to where the treasure is located. So that's part B. That's worth about 40%. And was pretty difficult, but was actually really rewarding, right? So I would say, and I'm going to do a review of all the projects in the class overall at some point, but to get ahead of myself for a minute, all of the projects kind of followed this, do the core thing in part A, and then use it to achieve something else in part B format, right? So like Kalman filtering, you were estimating where you are in this like asteroid field, and then that's the Kalman filter part, and then part B, you have to use those estimates of where you are, and then also neighboring asteroids to like bunny hop from one to another to get from A to B, right? And SLAM is the SLAM project, same kind of thing where we're building up a map, we have accurate estimations, and now we have to do something on top of it with it, right? And I feel like some of those were more relevant and realistic than others. This was really strong, right? Because it was a continuous grid space, so you don't want to do something like A-star, which we did in the last project, the search project, which I didn't enjoy much. Doing something like A-star or value iteration would be really, really hard because you're in this continuous space. There's orientation going on, so like not a bicycle motion model like we did in particle filtering, but there is some kind of motion model you have to account for. And you do have to get kind of creative and stand on the shoulders of that SLAM algorithm you built in the beginning. So if your SLAM is crap, whatever you come up with in part B is going to be crap, right? And I think that it was a really realistic manner in which this kind of system would be built. So kudos to them for that. But yeah, that's kind of the first main reason I liked it. How we had to extend it for part B, and also just in other ways, right? So as an example, we were given a distance and a bearing to the trees instead of like an actual estimate of where the trees are, and then by extension an estimate of where we are relative to the trees, like how much distance we have before colliding with them. So you have to account for all that extra math yourself, and it's not too bad. Like, it's just kind of some geometry. The angles can get a little gnarly, but aside from that, you're going to be fine. You're going to live, right? So we're building on this very basic, naive implementation of SLAM we did for like problem set 6, and using it as part of a larger system to navigate this forest, right? So that was pretty cool. Some of the unique things we had to do for part B were really cool. At least the type of algorithm I came up with was kind of like setting this initial guess that doesn't account for collisions, and then iteratively checking if we're going to collide on the path we're flying and changing accordingly, right? So that was a really interesting way to extend the super basic way we were taught SLAM in the lectures to this final project, which is pretty cool. That was the first main reason I liked it. The second reason I liked it is kind of the opposite here, right? So that first part I talked about was how we had to extend SLAM. This is more about how they structured the runners and like the file setup that we're given to test our code and whatnot. It was structured really well, and it was kind of, it broke up the different parts of the algorithm for us. So we had easy sockets in which to put the, different pieces, right? So there's like a process measurement step where you take in your measurements of all different trees and have to update your matrix according to that. Then your motion, right? So you have your motion command and your noise, and you update things in a different way. The ways you update and actually expand, because this matrix is getting bigger and bigger, the way you do that in the measurement section is very different from how you do it in the motion section. And then the get coordinates part, which is like actually solving for your map, right? And all of those are non-trivia. The linear algebra, and especially the indexing, gets pretty gnarly. And so I think that in this case, like giving us more structure, kind of constraining us a little bit, actually really helped me focus on implementing the core algorithm, which is pretty complicated compared to something like the Kalman filter from the beginning, right? So again, that was done really well, kind of in contrast to like the search project, which I've already ranted about enough, and even the PID project, which was, easy because it was small, but still a little disorganized in my opinion. But I'm biased because I love PID control. Anyway, really liked how they structured things in this project. And then the last piece, and in case you can't tell from my gaze, I have notes here. The last piece was about like the test cases, right? So SLAM, like I alluded to in the beginning of this, is only really necessary if you have noise. And so I think, again, contrary to some of the other projects, these test cases were very fair. They didn't, get into any weird edge cases or try to overload your algorithm, right? It was a reasonable amount of landmarks, a reasonable amount of navigation required to get from A to B, and they just injected like a ton of noise, right? And if you build a robust model, which we were taught how to do in a naive way in the problem sets, but now have to extend and make specific to this problem for the project, if you do that well, you will be able to handle it like most of the time. And so just to illustrate this example, I haven't really gotten into the code specifically because, from what I could tell, Georgia Tech's a little cagey about, student integrity and sharing things online or whatnot, but I feel like this is fair game. I actually had a direct motion model that didn't account for noise at all. So if I just did my, localization with this direct motion model, it would be a really crappy estimate that would drift over time because I don't account for noise at all, right? But I actually would use that kind of in two ways. The one way was if for some reason my matrix calculations got messed up and things were not invertible, which I don't think it's important to know. It's really important that you can invert this matrix representation of your map in order to solve for things. So it has to be like semi-positive definite. I always say that wrong. Positive semi-definite, excuse me. I would check if it was invertible, and if it wasn't, I would just use this direct motion model and continue, right? And that was just kind of like my stopgap of, I can handle a little bit of noise in this one time step and then get back to doing SLAM afterwards, right? The other way in which I use it, which is kind of more interesting, is I would use it to evaluate potential moves, right? So matrix inversion is a pretty complicated and compute-heavy operation. Even if it's positive semi-definite like ours are, it's still an expensive thing to do. And if I was doing that for every possible steering angle that I was commanding to my drone, it would add up really quickly. So I would basically say, is this likely to be safe in the no noise case? And I would also apply like a factor of safety to all the trees, make them bigger than they really are, to make sure we have kind of a buffer. So I would throw a buffer on it, I would ignore the noise and just kind of pray, and it worked really well. I mean, I got a 95, right? So the point I'm trying to get at here is just keeping it fair and implementing a realistic amount of noise. Also, fair is a bad way to phrase this. I guess realistic to what we've built is a better way to phrase it. Like appropriate for what we've built, but whatever. In any case, doing it that way, I feel like was really, really cool and allowed me to enjoy the fruits of my work with building the SLAM project. Versus, again, other ones like, you know, you would build the thing that you learn how to build, and then it's just a bunch of stuff that's like a giant pain. It's like, what am I doing? This is frustrating, right? So I didn't feel that way about this project at all, despite this one being pretty hard, and there being a few days where I would kind of sit down, work for 2 hours, and get nowhere, be more confused when I sat down, which is kind of frustrating. There were those moments, but overall, I really enjoyed the project, and I think it taught me things well. So overall, I would probably rate this project like an 8 out of 10. It was a strong, I don't know if that's the highest rating I've given anything, but I really enjoyed it. So I would give it like an 8 out of 10. I think that's fair. Great way to end the class, except for the final. So I have the final coming up. It will be everything that was on the midterm. So common filtering, particle filtering, PID control. Was PID control on the midterm? Maybe not, but histogram estimation, and then the new stuff, which was search and SLAM, right? And some other things in there too, like path smoothing or whatnot. And I think PID control might not have been in the midterm. Anyway, all this stuff, it's a cumulative final, is what I'm trying to get at. And so that will be next weekend. I'm not too worried about it. The midterm was, I don't want to say easy, but fine. I think the thing is, like, you go there and you implement these things from scratch, and it really forces you to understand what you're doing. But then you get to the midterm and the final, and it's like, true or false? And it's like, well, I've kind of sat there and banged out all the trues and falses up to now, right? I just worked on this thing for like 10, 15 hours. There's true and false. There's some multiple choice. Multiple choice get a little tricky, but overall, I'm not too worried about it. I just got to make sure I do well, lock in and focus, review all the stuff I might have forgotten for the midterm. And if I did my math correctly, I need a 75 to get an A, which I would obviously like to get. As long as I can scratch 75, I should be all right. But yeah, that's basically everything for the SLAM project. Overall, really liked it. We're kind of in the final hour of the class here, so I will definitely be reviewing it again soon, or not again, reviewing the class overall soon, which I'm actually really excited to do, and I'll probably do it in a much more formal way than I've had these vlogs be up to now. And then also, I have to start registering for my next class pretty soon. I have a big summer coming up in my personal life and with work. Excuse me. So I'm actually looking to take kind of a class that's just as hard as this one, if not a little easier. And I've found a couple of options. I think the main one I'm actually looking at is video game AI, which is pretty cool. Not something I expected to take this early, but I think it actually has lots of stuff I'm interested in, like coordinated movement between multiple agents, nav meshes, which is like a representation of terrain that you feed into, AI in a game or something, and like decision trees, finite state automata, another thing I always say wrong, things that I think I'll actually need going forward in my career for reasons I'll explain probably in the near future. So yeah, I'm pretty excited about that class. Hopefully I get in. Usually it gets close to occupancy, but not quite there. But yeah, hopefully I can squeak my way in. So thank you so much for watching. I am the Unhinged Engineer. I make professional development content for aerospace engineers, software engineers, people trying to work on AI and cool stuff. And if that's something you're interested in, or you're interested in this vlog of my grad school journey, I would highly recommend you subscribe, because this is definitely a channel for you. So thanks a lot for watching, and I will see you either in the next episode of this vlog or in one of my upcoming weekly uploads. So talk soon.